Hello, Physics 102 students. This is the one and only lecture on chapter 18. It's a little short chapter, and it really has maybe one very, very important result that comes out of it that we're going to be using over and over again. And it's got some other important aspects as well, too. But it's really about the kinetic theory of gases. And it is going to turn out to be probably, a nice way of looking at what's going on with these gas particles that we really can't see. And, this was very, very difficult for people in the 1800s when they couldn't see what was happening. They're trying to figure out what's going on with, heat exchange, and heat transfers. And you're dealing really with molecules and or atoms. These things aren't really visible to you. They didn't have really, the idea of electrons, protons, neutrons making up atoms and that sort of thing. But what I'm going to do here is treat the gas really like look at like one molecule and treat it just like it's a baseball or something like that. And so I'm going to remind you of some things that happened in Physics 101 with collisions, because, when you put gas or a mixture of gases, in some sort of container, they have collisions with the container itself. And so it's not like just a block of aluminum that you set, on the tabletop, or maybe it has only this one interaction with the tabletop. These gases are in motion, and, maybe by the time we're done, we'll have a good idea of really kind of like how fast they happen to actually be going here. And so let's just kind of take a look here at, some things that happened last semester with the idea of, just dealing with collisions. And, you should kind of be recalling at this point that there are, two types of collision. And, one type is elastic. And you probably had some exercises where you had, some sort of elastic collisions. And for the most part, unless you're really kind of dealing with very, very exotic circumstances, or you're dealing with these very small particles like we are in this case, elastic collisions are very difficult in everyday life to really sort of get to happen. So you might be able to get a glider and put it on an air track and put a very powerful magnet on it. And maybe the two gliders, when they're close, they can interact through the magnetic field and repel each other very nicely. In our labs, that's probably about as close as we're going to get to something that we call an elastic collision. Because an elastic collision, what you have is, momentum is conserved, but also the kinetic energy is conserved. And so you're conserving the energy of these objects that are in motion. So when they hit, they really can't, maybe a couple gliders on the track can get very close. And if they jiggle a little bit, well, okay, there goes some energy to this other jiggle motion. They actually hit and make a noise, and then you just lost some energy to sound waves and so forth. So it's very difficult to get this condition where the kinetic energy is really conserved on the scale that you and I live. Now, on the subatomic scale, two atoms really, for the most part, at regular normal speeds that we live at, and in fact, the temperatures that we live at, because it's going to end up here that temperature is almost the same as speeds. But so at the speeds that we live at, the temperatures that we live at, two atoms really don't hit each other. They don't actually touch, but they're going to interact through the electric field. So you've got this concept, right? You have this model of what an atom is like, and around the outside of the atom is the shell of electrons, these negative particles or whatever they happen to be. And so that cloud is negatively charged. And when you've got another atom, its electron cloud is negatively charged as well. So when they get close to each other, the two like charges will repel each other. And so they don't really quite touch. And so, maybe consider something like that as an elastic collision. Maybe, in this case, may be realistic. They certainly don't make sound waves or anything like that at all. And, you might be able to build here, kind of a simplistic model. And, eventually when you start talking about maybe bigger molecules, maybe like carbon dioxide, you got a carbon, you've got a couple oxygens, as that thing moves, it could be rotating. And so some of its energy may be translational kinetic energy, but it may also be rotational kinetic energy, where now you're looking at maybe the rotational inertia of the molecule. So now you need to be able to figure out the shape of the molecule. And so you can maybe do a center of mass, or, just do a straight calculation of, how that thing happens to be rotating. And so those things can be done. And but we'll start off with, just a simple, basically like a baseball. And that's going to be our molecule. And it's going to have these collisions. And, the other type of collision that you considered last semester was inelastic. And in an inelastic collision, get that right from here. In an inelastic collision, your momentum was still conserved as long as you don't put any outside net forces on the system. But the kinetic energy is not conserved. Okay, so let's say, for example, let me just put maybe EX right here. For example, let's say you have this chunk of clay here, and let's say it's like 1 kilogram, and you throw this at 10 meters per second, and it hits the wall, and it just sticks, right? So you got something like Play-Doh, it hits and it sticks. This is a totally inelastic collision. It had kinetic energy. Now it's stopped. It has none. And so, what takes place in something like this? Well, there's a change of momentum here, right? And so I'm going to call this right here my initial conditions. And so my initial momentum is the object's mass times its initial velocity. And so I just kind of chose some easy numbers, and I don't really want too many sig figs or anything like that here. I'm just trying to make a point. And so, this object has 1 times 10, or 10 kilograms times meters per second units of momentum to start with. Now, the final state here, there is no momentum, right? Now, something that I'm trying to remind you of from Physics 101 is that Newton's second law. The way we use it today is probably not how Newton would have probably published this in the Principia, 300 years ago, where we write it as the sum of the forces equals mass times acceleration. There's nothing wrong with that. But he was very keen on using the idea of a change of momentum here. And so, Newton's second law can be looked at as not only mass times acceleration, but that acceleration is really a change of velocity all over time. And I can take that change, the ddt, out here, and I've got this m times v right here. And that right there, m times v, right, that is the definition of momentum. And so Newton's second law can be certainly thought of as a change of momentum per amount of time, right? So this is the second law of nature, or the second law of motion, I should say. So there's the second law of motion. And so the change of momentum is important. And so when I take a look at what's taking place up here in our collision here, the change of momentum, and that's always going to be your final state minus your initial state, what you've got now, subtract off what you had before. So that's the way we always do changes. The change here is your final state, 0 kilograms meters per second, subtract off what you had before, 10 kilograms meters per second, and you have a change of minus 10 kilograms meters per second. Okay. So when you take at Newton's second law, that change is something that we can calculate, but it's proportional to the force, right? So I have a certain force that now just got imparted to the container. Eventually this will be a container holding the gas, but this chunk of clay imparted some sort of force here on the wall. Now, let's take a look at this situation where I've got a 1 kilogram ball and I throw this at 10 meters per second. And let's say that it has this, some sort of elastic collision with the wall. That would imply that it's going to bounce off and not lose any kinetic energy. So it's going to bounce off at 10 meters per second. Okay. So the question is there any change of momentum? There's a huge change of momentum here because momentum is a vector. And so we have to consider, really our directions here. And so my initial momentum is going to be 1 kilogram. And I'm going to call the direction here, that direction positive. And so I've got an initial momentum here of 1 times 10, which is just 10 kilograms times meters per second. Now, my final momentum is 1 kilogram, but the object is moving now in the other direction. And so my final momentum is negative 10 kilograms meters per second. And so when you take a look at this, I have a change of momentum here. That is my final state minus my initial state. And my final state is negative 10 kilograms meters per second. Subtract off what I had, 10 kilograms times meters per second. And so I get a change of momentum here that is 20 units in these kilograms meters per second. Okay. So if you hit and bounce off the wall, then there's a huge change. And I think, when we start building this idea of what gases are doing when they hit the wall, for these to be, some sort of elastic collisions, then, I think we're going to have to, in light of what Newton's second law says here, when you have a change of momentum, that implies that there's a force on the wall. And so these objects are hitting containers that are holding them. So if you've got gas, obviously you got some gas in your room that you're in while you're listening to this, those gas particles are hitting the walls. And for the most part, they're not flying through the wall, they're hitting the wall and they're bouncing off of it. And so when they do impart some sort of force. Now, if you contain the particles where they can't get out, then, that's something you're going to have to eventually start worrying about here in your physics and your model building and things like that here. Okay. So that's kind of the idea that I'm going to start with, is that these air molecules are some sort of like a little baseball and they're hitting the walls. And I'm going to probably just consider this being an elastic collision. And that may or may not be realistic, but as we kind of go through, we're going to make a number of assumptions, and that you just sort of hope that you end up with a result that is at least close in some senses to reality, at least close enough where you can make measurements and compare to your model. And if your model looks like it's behaving pretty realistically, then you might be onto something. And so that's kind of the road that we're going to be going down here. Okay, to start with here, let's say that we've got a gas contained maybe like in a box. And so, let's say that, the box starts kind of looking like this here. Okay, so you've got some sort of box, and I'll just call it the x-axis, the y-axis, we've got the z-axis, and I'm going to have this object inside of there, and it can, hit a wall now and then. Okay, now it can obviously hit the top and the bottom of the wall as well as the sides. I'm just going to kind of consider right now what happens when it hits like one of the sides. And eventually then I'm going to then say, well, I've got a whole bunch of these things in there, and what's really going to be the end result of having a whole bunch of collisions here. So let's say that this thing actually comes in and hits the wall, hits this wall, and then bounces up this way. Okay, now one assumption that I'm going to make here is that I'm going to assume, since it hit this wall over here on the right-hand side of the box, that the wall cannot change the velocity in the y direction. If it can, then it's kind of doing work on the object, and then I'd be asking the question, well, what's the mechanism for work to be done here? So I'm going to assume, that the wall does not change the velocity in the y direction, because maybe it came in here with just a velocity in the x direction, and so it's going to leave with the same velocities in the x direction. And I'm going to probably assume here that if it continues as I've got it drawn here, it's going to eventually hit the top of the box. So I'm going to assume that the top and the bottom of the container does not change the velocity in the x direction. Okay, so the walls, really here aren't speeding these things up and slowing them down here. And like I said, that this may or may not be a realistic model that we're building here, but you just have to kind of, play through the physics and see what you end up with, and we'll just kind of go from there here. Okay, so let's say that we have this collision right here. I'll put a big green dot right there on the edge of the wall, and what does the physics say that we can really sort of say with some certainty there? Well, there's a force now coming from the wall, and that is the change of momentum per change of time. Okay, so that's just Newton's second law. And so this thing is going to hit the wall, it's going to bounce back, and just like the example we had up above here. So really kind of take a look what's happening. It came in with 1 kilogram times 10 meters per second, or this 10 kilograms meters per second amount of momentum, and it leaves with the same amount. The only difference is that there's a change of sign here, right? But overall, the change of momentum is twice the initial momentum, because of the change of direction. And I know which way the force is here, so I'm not going to really worry too much about that minus sign here, right? And so, what I've got here is 2 times the object's mass times its velocity in the x direction, all over the change of time. Now, I could already see that the change of time is going to be a problem for me because once again, I really don't see these little gas particles hitting the wall and bouncing off. And now I'm considering, how long does that collision really sort of take for it to, hit the wall and then, change its direction and so forth. And trying to build some sort of device to measure that, may or may not be easy, especially 150 years ago when you're kind of coming up with this kinetic theory of gases. So that delta T, in other words, is something I'm going to consider working on a little bit to kind of get rid of it. And probably the best way of doing that is, let's just say that this box has got this dimension here, we'll call L here. And so if the particle goes from one side and then comes and hits the other wall, the distance that it travels is 2L, and it's traveling at some speed. And then I've got some time for it to do that. And so, maybe I consider that 2L all over the velocity in the x direction is the amount of time that it's going to take to go from one wall to bounce off, hit the other wall, and then, do 2Ls to come back to that same spot here. And so it at least gives me a fighting chance of getting rid of this delta T here. So I'm going to put in 2L all over the velocity in the x direction and kind of see what that leaves me here. And I kind of notice that, the 2's cancel, and I've got a Vx times a Vx here. And so what I really have here is an M Vx squared. And then on the bottom, you're just left with this L here. Okay. Now, this is for one collision on the wall for one meatball, right? One meatball hit this wall and bounced off, and it did so elastically, right? So I'm assuming right in here that this was, elastic collision, just like above in that example. Okay. So we had to squirm around a little bit to get rid of that delta T, and I could write that in terms of, the size of the box, which is maybe not bad because, a lot of times when I start looking at gas laws and so forth, they've got a volume in it, right? And I could start, writing the volumes of this container down in different ways. And it may turn out that we may need to be able to do something exactly like that. But this is not bad, right? I sort of like this, going right to fundamentals, forces, a conservation law. This is good, right? When you can't see stuff, you always go back to your basics when it comes to your model building. And so now what you have to probably do is consider what are we on? Number 2 there, so let's call this number 3. So number 3, what we want to do is find the net force by all the molecules in the sample. Because what we have above is for one molecule. Okay, and so this is where we have to kind of think about this a little bit here. What exactly is going to take place? And so you really have the particles in there. And once again, I think I'm going to have to make some assumptions. And probably the more particles you have, probably the closer to reality that these assumptions are going to be. But the force on this wall really in this x direction. So I'm just kind of considering these particles just kind of moving sideways right now. And I'm just looking at my results up there. It's m over L. And then there's this velocity in the x direction squared, right? So now if I have a lot of molecules, well, I'm going to get the velocity of the first one in the x direction squared plus the velocity of the second one in the x direction, and I have a squared, and the velocity of the third one in the x direction, then I have a squared, plus the velocity of the fourth one in the x direction squared. And I'm just going to add them all up, right? So I might have, a Brazilian of these particles in this box, but each time when one of them hits the wall, they're all going to probably eventually hit the wall here. I'm going to just add up all of those collisions that are taking place at one time. And that's going to be the force on, by all the molecules at one time. And so, we could probably write this, considerably simpler. Just by probably saying m over L, and then saying, well, okay, we have n particles or something like that. Okay. And so I could just say, well, I've got n particles with some sort of velocity in the x direction squared, and I'll put a little bar above it that's going to indicate, well, just take the average velocity. When I say average, I really mean average, right? Some of them might be going, 10 of something, and some of them may be going 15, some may be going 20, and you really just sort of add them all up and just really kind of find the average here. This is not average speed. We get total distance over total time or anything like that here at all. Now, here's where we have to kind of consider really what is taking place here with these velocities here. And so I'm going to probably have to make another assumption here, because when I look at this, that's where we have to kind of think what exactly is taking place with these velocities. And I'm going to assume that the velocities are just random. That may not be true, right? If you have a gas sample and you have a fan blowing on them and you're moving an entire mass in a certain direction, well, now they're not random, right? And now you're doing some work on them, and you're pushing them in a certain direction. But this is just a box. It's just got, it could be a shoe box. It's got some gas molecules in it. And I'm assuming that there's just as many moving this way as there is that way, as there are kind of, moving towards you and so forth. So, we have these three directions that they have, 3 degrees of freedom. And I'm just going to expect here that, we just have something here that is totally random, which would really kind of mean that the average, a little bar means average, velocity in the x direction is the same as the average velocity in the y direction. That's the same as the average velocity in the z direction. So if they're random, then they're just moving in all directions the same amount, right? So they're just doing something all kind of crazy. And we're not pushing them. We're not trying to do something and doing work on them or anything like that here at all. And so if the velocities are random, then really all the squares of these velocities are certainly going to be random here as well. And so here's an assumption that really kind of makes sense if you are doing really kind of no work, on these particles or anything like that at all. And then if you really, let me see number 3 here. So if we're really kind of considering what is taking place here. So you've got a particle, let's say this is the velocity vector. It's got some velocity in the x direction. It's got a component in the x direction. It's got a component in the y direction. And it has some component in the z direction as well. And so the velocity vector, typically we would probably write that as, how would, in the picture that I've got right now, the velocity vector is the addition of these two components, right? The x component and the y component. So you put them head to tail, and what you do, you get the x component, you square it, you get the y component, you square it, you add them together. You take a square root, but if you have a third dimension, you're going to square that as well. And but since I really kind of have random particles here, I'm going to address these y and z components really being just about the same as the x component in terms of their size. And so the magnitudes of these components are all the same. And so my average, or my velocity vector here, the size of it is probably about the same as 3 times the x component squared on average. And so, if the y and z components are the same, then, I could just sort of say, well, okay, one component is as good as the other component, because I'm really kind of looking above what we've got here, the force in the x direction. And but the situation is really more complicated than just looking in one direction here. So there's really the 3 dimensions to consider. Okay. This is why when it comes to gases and so forth, you typically don't see people talking about delta T times. You don't see people talking about forces in the x direction because, or in the y direction, the z direction. You really have this huge conglomeration of particles, even in something the size of a shoebox, that are all doing something, unless you're doing work on them, something very, very random. And so it makes more sense to bring in some of these other concepts. And the concepts are closely related, but this is why you see people start talking about something like pressures and stuff like that, because pressure is force per area, and that probably starts making more sense when you can do things per something else, when you have a lot of different things here. And so that's number 3 here, so I'm going to try to keep that right there so I can see that. And let's bring in this idea of pressure. Let's see what this tells us here. So pressure is defined as force per area. So this is exactly the same pressure that we saw back in chapter 13 or anything like that at all. And so now I've got something up above here for force, right? I've got this M all over L times how many particles I've got times this average velocity in the x direction. And so I'm just going to kind of copy that down, that my force is really this M per L. So it's not something I would have memorized or anything like that at all. And then I've got this N, and now I've got this velocity in the x direction. And I think I'm going to take that out, and in its place, I'm just going to have the overall average velocity divided by 3, right? So if I just kind of bring this 3 over here and divide both sides by 3, I can read it, write it like that, and it's squared, right? So that velocity here is, it's got this little square on it. And then I still have the area down here, so don't forget the area. Okay, so when you take a look at that and you start wondering, well, did you really kind of make things any better or anything like that here at all? But maybe so, because what area are we talking about here? Well, we're just considering, when I kind of go back here, I'm just considering what's happening on this wall right here. So that wall would have this area A, and then I introduced early on this length here, and I kind of see them both showing up here. And if I get that area and I multiply it by that length, the size of the box, that's really the volume of the box, right? And so this is why these things kind of keep popping up here. And so what you really have here, if I have length times area, that's volume. And so I've got P times V, because those two things multiplied right there. L times A equals volume. So multiply both sides by volume. And what you have here then is N, how many particles you really have. You've got mass, you've got a 3, and you really kind of have this average velocity of the particles squared here. Okay. And so I'm really kind of liking what I'm seeing here. So this is looking pretty good. And so once again, let's kind of go back to physics 101, because you're seeing something here that almost looks familiar, right? You're almost kind of seeing something in here where you have an m and a v squared. And you saw that before, and it's really a very important concept, especially when you smash a 1/2 out in front of it, because now you're talking about energies here. Right? And so this is the kinetic energy of some sort of object here that maybe is not rotating or anything like that here at all. So I think I'm going to introduce that 1/2 here, and well, why not? So I've got a P times a V. And, let's just kind of leave these other things alone here for the time being here. I've got this N all over 3. And what I really want here is a 1/2 mv squared. And so if I put in a 1/2 there, I'm going to multiply here by a 2 so they cancel out. And I have, exactly what I really kind of had here before. And this looks pretty good to me here. Because you also have this idea that, let's maybe kind of get this set off here, that we might want to recall that in our background we have PV equals nRT, where that N is really the number of moles. And you also have PV equals capital N KT, where that's the number of molecules. So capital N, the big N for the big number, right? A lot of molecules and a number of molecules. And so when you kind of get all these different aspects of the motion of these objects and kind of start putting it together here, this PV right here can be thought of as an N times a K times a T. So we can really kind of substitute that out. And, what's really kind of, left over here. Well, over here, we've got an N. There's this 2, there's a 3 down here. And I kind of want to leave this really kind of alone because that's really kind of, magical quantity of 1/2 mv squared here. And so what's really kind of left over here in our algebra? Well, the number of molecules look like they really kind of cancel out. I'm going to multiply this 3 over here, 3kt, and this other 2 will come over here, equals something like a 1/2 mv, and that's the average velocity squared. And this right here is really the result that is important in chapter 18. And take a look at that result here. So I'm kind of glad this really kind of worked out the way it did. But what it tells you is that the average kinetic energy on one side of the equal sign equals, there's some constants there. There's 3/2, there's a K, and there's a T here. But the energy of the object is proportional to the temperature. That is very important. That was not ultimately clear to most people in the 1800s. Today, it's just something that we just really kind of take for granted. That when you say something's going fast, it has a lot of kinetic energy. That's almost the same as saying that it has a lot of temperature. And so when you put a thermometer in a sample of liquid or water or gas or whatever it happens to be, and you find the temperature, what you're really doing essentially is finding an average velocity that the particles have. And so when you've got your thermometer someplace, and say it's in a sample and particles start hitting it. If they're going fast, then they have a pretty good collision with the objects. Maybe it's an old time mercury thermometer. The mercury particles then get sped up by how fast they're going, and so the faster they go, they got to find a place to live, and so they start going up the tube. If your particles out here are going slow, and then they're very, very lethargic collisions, and not much is happening then to the mercury, and so it can take a small size here. But this is important here, that the average kinetic energy is proportional to the temperature. Okay. And probably eventually the physicists will look at this result here and, start looking at maybe something like this as, okay, what is that 3? Why is that here? Well, and that's really because, these particles are moving in 3 dimensions, right? So they have 3 degrees of freedom here. And, but that really is what you want to take away here, is that the temperature, T, is proportional to kinetic energy. When one doubles, the other doubles. When one triples, the other triples. And so these are, very important ideas of what's really kind of taking place here. Now, there are probably a few, but not a lot, vocabulary that shows up in this chapter here that, I kind of want to call your attention to. And let me kind of see where I'm at here. This is number 4. So let's call this number 5 here. And that's this idea that we've been kind of skirting the issue here, this idea of heat. And, what is heat? At this point, heat is really going to be a transfer. This is a process. And there's different ways that this process can take place. And we'll take a look at some of those details here in a chapter or 2. This is a transfer of energy, kinetic energy, from one object to another. This was a very difficult concept in the 1800s. Exactly what is heat? I mean, when you get a water sample that's 50 degrees and you have a water sample that's 20 degrees, and you get them near each other, maybe you connect them with a piece of material, maybe you get a big chunk of aluminum, and it kind of goes and dips in one and dips in the other. The one that's at 20 degrees, the cooler one, will start warming up. And so there is some process where the energy is going from, one water molecule in one container to, some other one here. And so that's something we're going to have to really worry about here. And this idea here now of temperature. And, this is really going to be the measure that we just saw here of the average kinetic energy of really, individual molecules. And so making a measurement of a whole bunch of them is going to be, much simpler than just doing something like one of them or something like that. Okay, now this is something that we won't use too much in chapter 18, but we're certainly going to bring this into play in chapter 19 and 20. This idea of internal energy. And when you've got this shoebox and it's filled with particles, we're going to use this idea of internal energy to really mean the energy of all the particles inside of there when you can add them all up. Okay, and so if they're just really moving randomly and so forth, that makes life actually much easier. Otherwise, we have to have a lot more details about the work that we're doing on it. But this is going to be really the total energy, of all molecules. Within a sample, whatever that sample happens to be. Okay, This internal energy, we probably have some different ways that we can kind of find this here. But looking above here, we have this 3/2 kT. And if you were to look at these two things right here, this capital N times K times T is the same as little n times R times T. And so this internal energy, we may have different ways that we can kind of write this here, but I think your book for the most part is going to want to put it E, and then you'll put it INT, which is implying that this is probably not one object, right? This is the internal energy, which really means it's a conglomeration of a bunch of particles that are giving you this total energy here. And that's going to be this 3/2 that we see up above with an N, K, and a T, or it could be 3/2 N, R, T. So we know that it is going to be proportional to the temperature in all cases. And this is how we're going to find it. So we can do it really per mole, the little n, or we can do it with all of them added together, right? So when this little n here is still the number of moles. So it doesn't matter if you're dealing with moles or if you're dealing with number of molecules. We can probably take care of the situation. Now, what if we have, a simple case like, in the room that you're in, probably something like close to 80% is today, probably 80% dust particles, but let's say it's 80% nitrogen and 20% oxygen. And say it's at room temperature. So let's say that the temperature that you're dealing with here is, room temperature, something close to 20 degrees. How fast are those particles going? This is something that we can, do right now. And so, something like chapter 18, it gives us an idea of how fast these particles are going that we can't see. And eventually, we'll be using that information to do something probably more important than just how fast is a particle going. Eventually, this is going to have to lead to the idea of people building engines and things like this. And so let's kind of see how to use this here. So, for example, let's say you have an oxygen molecule, so O2, at something close to room temperature, say like 18 degrees C or something like that. What's its speed? Can we, actually sort of do that? And we can, but when I take a look at what we have, up above, we do have to worry about, looks like, sometimes mass kind of shows up here, right? And so, you have a 1/2 mv squared on one side and you have a 3/2 kT on the other side. And so if you want to get that velocity by using what I've got kind of outlined here in yellow, the 1/2 will cancel out. And so, a lot of times people will look at this right here to get an idea of how fast things are going. If we cancel out those 1/2, what you've got is a 3, a K, and a T divided by M. If I take a square root, that's the average velocity. Now your textbook is going to even make it more complicated looking. It puts an RMS here, which really means root means square, which means that we're really just kind of using the average velocity here. And so K is a constant we can look up, not a big deal. Somebody told me the temperature, not a big deal, but what's the mass? What's the mass of an O2 molecule? And so now you may have to look in the back of your book, and I think it's Appendix F. And so I've got my book open here, so I can kind of look up some of these things here too. But, mass of an O2 And O2, oxygen is really 16 grams per mole, and there's really, two of these connected together. So you really have 32 grams per mole. I really just want one. And so what we use here is something called an atomic mass unit here. And an atomic mass unit is close to the mass of a proton and a neutron here. And you can just kind of think about this as a conversion here. And you may have to use this conversion quite a few times in this chapter. So this is what we call, the atomic mass unit. So in O2, there's a lot of ways to think about what that is, 32 grams per mole. But that's also, there's like 32 particles there. Oxygen is number 8. And so it's 8 protons. It has 8 neutrons. So there's 16 of them. And so there's 16 in one molecule or one atom, and there's 16 in the other. And so you have 32 of these particles. And so the atomic mass unit is not really the average, but it's like that. And so this is going to be really identified with carbon-12 being exactly 12 grams per mole and so forth. And so this is where this kind of average atomic mass unit comes from. And so this is going to be a conversion that you're going to have handy here for chapter 18. And, I kind of think when I multiply those out here on my calculator, 1.66 is the atomic mass unit times 10 to the minus 27 times 32. And I end up with something like 5.31 times 10 to the minus 26 kilograms is the mass of O2. Okay. Now, if you want to find out how fast that's going, then you're going to be using, this up here. What I've got in green, you're going to get 3 times K times T, but you got to know the mass of the object that you're talking about. And so K is the Boltzmann constant, and you've got that right in the front of your book. So I think what I'm going to do here is take a peek at that. I'm going to get 3. I'm going to look at, I got the back of my book open to get that, those numbers for oxygen. And now I'm going to look in the front of my book to get K. And K is 1.38 times 10 to the 23 with a minus sign times 10 to the minus 23. 1.38 times 10 to the minus 23 is right in the front of your book. I'm going to times that by 3. I'm going to times that by the temperature. Now the temperature is 20 degrees, but you got to add 273. That's going to have to be in Kelvin. So times 293, I'm going to divide by this crazy mass that we have down here, divide by 5.31 times 10 to the minus 26, and then you have to take a square root. And I'm getting something very close here to, maybe 2 or 3 significant figures of something like oxygen O2 at room temperature at 20 degrees is moving something like 480 meters per second. 480. I'm really getting 478 meters per second here. But try that and make sure you can get that calculation going on your calculator the right way. So you got to do a little bit of work to get the mass because that is going to show up in the denominator here, but you're going to get 3 times the Boltzmann constant. You'll have that in the front of your book. That temperature needs to be in Kelvin because the Boltzmann constant is going to be in Kelvin. And so you got to get 20 degrees, add 273 to it. So that'll be 293. Divide by that mass. Don't forget to take the square root. And this seems about what I remember, that at room temperature, air molecules, mostly oxygen and nitrogen are moving something close to something like 500 meters per second. And so the calculation tells us, something like this. Okay, so we had a lot of assumptions here, really to end up with, really kind of what's in yellow right there. And is that, something that's going to be realistic? For the most part, this is going to work pretty good until the gases start getting complex. When they get complex and their energy is not just translational kinetic energy, like this, little meatball I had hitting the side of the wall here. But if they're rotating as well, then maybe our model will start not being as close to what we measure it as we would really like. But there are ways to take care of that. So we'll be able to do that too. And so, what's there in yellow is really what you want to take away from chapter 18. That's really an important thing, is that the average kinetic energy of a whole bunch of molecules is proportional to the temperature, right? If you measure one, you're essentially measuring the other one. And so that's going to be important. And then you've got some of these definitions here of what we really mean by heat, right? This is going to be heat is going to go from one object to the other. And eventually it can do that through radiation. It might be able to do that through convection, might be able to do that through conduction. And we'll take a look at some of those heat transfer processes. And so what we have up there in yellow is exactly, the end result here of kind of a simplistic look at what happens when a molecule hits the side container of a shoebox or something like that. And it leads us to this letter B here, temperatures, the measure of the average kinetic energy of individual molecules. And that's exactly what we've got here, right? And then, we're going to have to put that all together with this idea of internal energy, and that's the energy of a sample of gas. And so when you're building something like a heat engine, you're going to have probably gas in some sort of cylinder. You're going to get it hot. You're going to, explode some sort of gasoline or something like that. Get this hot so that it can change size considerably because you changed its temperature. When you change its temperature, you change how much energy is stored in it. And that energy that's stored in that sample can be used for work. It can be used to move a piston. Once the piston moves, you can then put that on a crankshaft, which then starts turning, in some cars like a flywheel, and the flywheel is turning something else, and eventually your tires are rotating, and now you're going down the road. So we're getting close to this idea of heat engines, but it's still a couple of chapters away. But this result here of this internal energy is something that we're going to take from chapter 18. We're going to use it there. So there's some considerably interesting things that could be done with the kinetic theory of gases. Now we're going to kind of keep dipping our toes back and looking at this and maybe making things a little bit more realistic as we go on, especially if the gases start becoming more complicated and so forth. So eventually we'll have to take a look at what happens when the volume of a gas changes by maybe keeping the temperature and the pressure constant, and then look at what happens to the other parameters as well. And it may turn out that we may have to make some adjustments to the model if the gas is monatomic or diatomic or even more complicated, right? Where you've got a lot of different atoms connected to it and so forth. But there'll be ways of dealing with that, and so we'll take those as we kind of go. So this is really the main idea that comes out of chapter 18, and it's all really right there in yellow. Temperature is proportional to the average kinetic energy of a molecule here, and so that'll be an important result that we take forward. So hopefully this kind of helps you go through some of the sections. Right, not all of chapter 18 is really assigned to you, but a few of the important ones are that we're going to be using. And then we're also going to be starting chapter 19 here, and so 19 will be broken up into some different parts. So take a look, what's posted on Canvas to kind of see how to break 19 up. So we'll have several different lectures on chapter 19, so I'll probably take a look at specific heats and specific heat capacities and mixing things, and we'll take a look at these heat transfers and things like this, and how gases can really sort of do this, and probably the change of phases as well. So there's plenty there still for us to kind of be looking at. So remember, we started this process. It really had to do with what happens when you add energy or heat to an object. It may, and what can it do? Well, it could change size. And so we kind of took a look at solids and liquids. It could change size. And if it's complicated and it's a gas, and we have this ideal gas law. And here, if we add heat to it, it could change temperature. So we haven't really discussed that yet. And so that's really kind of lurking here, and we're going to have to take care of that probably right away here. So hang in there, work through a couple of these sections here in chapter 18, see if you can get these to make some sense. And then also start immediately into chapter 19. So there's some very nice physics working there. So hopefully this helps you going, and I'll see you soon. And so bring your questions to discussion, and we'll kind of see what's taking place here. So I'll see you soon.